This document contains 321 technical questions. It is a massive, concentrated dataset designed to test advanced Node.js engineers during technical interviews. To a junior developer, this list appears to be a collection of trivia to be memorized before an exam. But for a senior engineer, these questions serve as a probe, used by interviewers to map their understanding of the runtime's physical limitations. A macro analysis of these questions shows they cluster around three specific architectural boundaries. First, mastering the micromechanics of time within the event loop. Second, surviving memory pressure through active flow control. And third, bypassing strict single-threaded CPU limits of V8. Success in a senior engineering interview requires reverse engineering these three pillars into a single, unified mental model. We begin with the first cluster, the mechanics of asynchronous timing. Question 31 identifies a recurring requirement. The engineer must differentiate the execution order of process.nextTick, setImmediate, and setTimeout. This tests your knowledge of the Node.js event loop phases. The loop moves through a strict cycle: timers, pending callbacks, the pull phase for I/O, a check phase, and finally close callbacks. The setTimeout function schedules a callback to execute during the timers phase at the beginning of a cycle. setImmediate queues execution for the check phase, which occurs after standard I/O in the pull phase has been processed. But interviewers specifically look for an anomaly: process.nextTick. This function targets the microtask queue. It operates as a prioritized bypass lane that sits between every single phase of the standard loop. Crucially, the event loop cannot advance to the next phase until the microtask queue is completely drained. This creates a dangerous failure mode. Recursive nextTick calls can trap the runtime in the microtask queue, resulting in catastrophic I/O starvation, where the server stops responding to new requests. Explaining the difference between these three functions proves you can orchestrate precise timing without blocking the server's primary loop. The second architectural boundary centers on strict memory management. Question 171 introduces the concept of back pressure, which addresses the trade-offs between buffer-based and stream-based data processing. In many basic implementations, code reads an entire file directly into system memory before beginning any processing. As traffic scales, these large memory allocations quickly exceed the V8 heap limits, leading to an immediate process crash. Streams solve this by chunking data into sequential pieces, allowing for the processing of massive datasets without ever filling the V8 heap. However, this creates a speed mismatch when a fast data source feeds a slow data consumer. To manage this, Node.js uses an internal holding buffer. The fast producer pumps data blocks into this buffer, and the slow consumer pulls them out at its own pace. Because the producer is faster, the internal buffer eventually fills to capacity. This specific capacity limit is defined by the high watermark setting. When the data hits the high watermark, the system sends a pause signal backward through the pipeline to the producer. This upstream feedback loop is what we call back pressure. Mastering streams requires an engineer to orchestrate active flow control to prevent silent, runaway memory bloat in production. The final constraint is the most rigid: the single-threaded nature of the V8 runtime. Computationally intensive tasks like image processing or encryption monopolize that single thread, halting the event loop for every other user. Question 228 asks for a comparison of the child process and worker threads modules to resolve this bottleneck. The oldest scaling strategy is the cluster module. The cluster module works by cloning the entire application process. A master process routes incoming network traffic to these isolated Node.js instances. Each clone requires its own separate memory allocation, which introduces significant system overhead. This architecture is ideal for scaling network I/O throughput across multiple CPU cores. For pure computation, the modern alternative is the worker threads module. Worker threads run inside the same process and communicate through a central shared array buffer. This allows multiple threads to perform heavy computation on the same data simultaneously, without duplicating memory. Thread-level scaling handles massive compute loads without the memory costs of process isolation. Knowing exactly when to choose process-level isolation versus thread-level shared memory determines if a system can scale under high CPU demand. When we step back from these individual mechanics, the bigger picture becomes clear. These three models interlock to form the complete architectural schematic of a production-grade backend. The hundreds of questions in the dataset are simply different ways to verify an engineer's fluency with this schematic. This unified mental model is what the interview is truly testing. Senior engineering roles require the architectural management of a highly constrained runtime environment. Every line of code must be written with a clear understanding of the physical boundaries of the underlying system. Success depends on protecting phase priority in the event loop, controlling data flow limits through backpressure, and routing compute loads to the correct execution context. Mastering this topography allows an engineer to build resilient systems that maintain consistent performance under extreme production traffic.